Hello everyone, my name is Garcia Soto. I'm a postdoctoral researcher at IST Austria, and in this video I'm going to present an automatic approach for synthesizing linear hybrid automata with affine dynamics from experimental data in the form of time series. This work is in collaboration with Tom Hensinger and Christian Seeling. We find the general model synthesis problem interesting because many sciences such as financial, cognitive, and biological sciences pursue to understand the mechanisms of real systems and make this understanding accessible by constructing models. The construction of these models is usually performed by experts in the corresponding field. These experts does not only propose hypotheses and design experiments, but also evaluate and interpret the data. Therefore, the analysis can be driven by the bias of the expert. Besides that, in the case of the hypothesis is wrong, the experiments become useless. In order to avoid such a bias, possible misinterpretations, futility of experiments, and enabling the processing of large data, automated approaches are developed. Our high-level goal is to fully automate the model synthesis. Concretely, we present a synthesis algorithm based on membership queries whose input is a specification in the form of time series and its output is a linear hybrid automaton with affine dynamics. We are interested in models whose behavior is driven by the interaction between continuous and discrete dynamics. Such kind of behavior is captured by hybrid automata, and we focus in a particular class. Let me show you an example of hybrid control system in this class, where the physical elements exhibit continuous behavior, while the implemented controllers, which correspond to the software elements, exhibit discrete behavior. Here we have a cruise control interacting with an automatic gearbox, whose goal is to set the velocity of the vehicle to that of a user-specified velocity. The gearbox receives the torque from the engine and appropriately sets the velocity depending on the current gear. The cruise control receives the current velocity and automatically sets the gear. This system can be represented formally by a hybrid automaton with affine dynamics, which consists of one mode for every gear position represented by these boxes. The dynamics in each of the modes are captured by different linear differential equations, and the mode switches are captured by edges. Executions of this kind of automaton are piecewise affine functions. Observe that the hybrid automata model is appropriate not only for describing embedded or cyber-physical systems, but also for describing biological systems, where the evolution of the system sometimes depends on value thresholds of certain variables. Our synthesis algorithm is an adaptive synthesis algorithm that constructs a model for an initial data set and iteratively improves the model when considering new data, while ensuring precision guarantees in the model. The construction of the model relies on the membership query of piecewise functions approximating the data, and this membership query is performed by a reachability analysis. Our approach consists of two main steps. The first step fits the time series data to a piecewise affine function such that its derivative is equal to a matrix A times Ft plus a constant vector B, where A and B differ for each piece in the function. The second step constructs a hybrid automaton from the piecewise affine function. And the constructed model is such that for every function f, there exists an execution in the model such that the distance between them does not exceed a given value epsilon. In the first phase of our algorithmic framework, we construct a piecewise affine trajectory from a time series S, where we consider in switching points of the function f from the set of points in the time series, marked here in orange. Then we need to find an affine dynamical system x prime equal to ax plus b and an initial state x0 such that the solution f satisfies that the norm of s minus f is less than or equal to delta at every time, while maximizing the time domain for the same solution. We solve this problem with a query to an optimization tool in combination with an ODE solver, and maximize the time domain using binary search. The second phase of our algorithmic framework is to construct a hybrid automaton model from a given piecewise affine function f, a model h, and a positive value epsilon. We say that the model epsilon captures f if there exists an execution in h that belongs to the epsilon tube around f. We initially check if the function f is epsilon captured by the given model. In the case that it is captured, the model remains as it is. Whereas if the function is not epsilon captured by the model, this needs a modification which will consist on relaxing constraints or adding modes and edges to the model. Note that the epsilon value is a trade-off between the size and the precision of the model. Let me first introduce the membership query. Formally, we say that the model epsilon captures a function f if there exists an execution sigma in the automaton such that the distance between f and sigma is smaller or equal to the fixed epsilon. We have no result about complexity of the membership query, but we can claim that it is not a trivial problem. Hence, we reduce the membership query to a subset of executions by considering synchronous time switches for f and sigma, which result in an execution with the same number of pieces as f. We solve the membership query by means of reachability computations. In practice, what we want is to compute what we call the synchronized reachable set S-reach. S-reach is determined by the precision value epsilon, the piecewise affine function f, a polyhedron p, and a path in the hybrid automaton p. We consider an epsilon tube around the function f, a path p in the model with the same number of modes as pieces f has, and this path p sets the dynamics to be followed by the execution sigma. The polyhedron p considered is the epsilon tube at initial time, and we denote by R0. S-reach is computed by following the dynamics determined by the mode path while being keeping inside epsilon tube. We denote by R1, R2, etc. the reachable set at the switching times. And the final reach set corresponds to the S-reach that we want to compute. Formally, S-reach defines all the final points x for execution sigma, switching synchronously with f, starting at p, and always inside the epsilon tube. Observe that S-reach it is computed by iteratively compute the sets Ri that correspond to the synchronized reachable sets for every single piece in the function f. The challenge here is that S-reach cannot exactly be computed. And our solution computes in a forward and backward function over and under approximations of the synchronized reach set. We first compute an over approximation of S-reach, which in case of being empty, results in a negative membership query. This will be the case for most of the paths in the hybrid automaton. In the case of obtaining a non-empty over approximation, we compute an under approximation of the reach set. Observe that a non-empty under approximation results in a positive membership query. For the case where the over approximation is non-empty and the under approximation is empty, we perform a contraction in the over approximated sets. Finally, when obtaining a negative membership query, we proceed to the model update to ensure that the given piecewise affine function is captured by this new model. So the goal of this procedure is to modify the model for capturing the piecewise affine function while satisfying optimal guarantees. We say a model is optimal when having the minimum number of modes and transitions. Observe that the possible model modifications are to relax the constraints, defining invariants and guards, add transitions, and add locations. We keep track of all of these modifications by defining the tuple mode. And we reason about an optimal model by considering a lexicographic order for the mode tuple associated to a mode path. So we select the path that optimizes the number of updates by constructing and exploring a tree of modified models, so-called exploration tree. An exploration tree is constructed for a given piecewise affine function with k pieces and a hybrid automaton model of having m modes. It contains k layers, one per function piece, and every node has m+1 children. Every node represents a model modification associated to a concrete mode path. The root node represents no modification at all, and we represent it with an empty path. Other nodes correspond to modifications associated to the added mode, such as relaxing invariant and guard constraints, or adding an edge in case of non-existence, or adding a new mode to obtain membership true. Computing every updated model is not efficient, so we introduce a decision strategy to partially explore the tree. Let me illustrate the decision strategy in the following concrete example. We have a function here of 2 pieces and a hybrid automaton model with 2 modes. The root node of the exploration tree corresponds to the empty path and includes the initial model, and here we observe the mode tuple with non-modification. The first piece of F follows the dynamics x prime equal to minus x for 0.5 time units. The available choices for the first automaton mode are Q1, Q2, or a new mode, Q3. Hence, the root node expands to 3 new nodes. The node with path Q1 requires a modification of the invariant of Q1 because drilling in that mode for 0.5 time units is not possible otherwise. However, since the final reachable states do not intersect with the epsilon tube, we get a negative membership query. So this node status is deactivated and none of the child nodes will be explored further. The node with the new location Q3 has a location entry. So this in the modification tuple. Whereas the node with path Q2 does not require any modification and hence is chosen as the next node for exploration. Now we consider the second piece with dynamics x prime equal to 2x for 0.7 time units. Again, we have the choice between the existing locations and a new location Q3. The exploration works like before, only that this time we need to add a transition from Q2 to the next location in all 3 cases. That will be this one in here. The left with the path Q2, Q1 has the highest priority and we perform a membership query for it. In this case, the query returns a positive answer and the algorithm outputs the automaton H4, which looks like H but with an additional transition and an extended invariant in location Q1. We implemented our approach in HiSynth, where we wrote the high-level synthesis algorithm in Python and the low-level algorithms in Julia. We have evaluated the implementation in 3 different benchmarks: a heater, a gearbox interacting with an automatic cruise control, and in electrocardiogram signals. For the heater and the gearbox models, we simulated the time series data, whereas for the ECG signals, we borrowed data obtained from the Physiobank database. Here I show you the benchmark results. The second column shows the allowed error epsilon between piecewise affine executions and the model, or the allowed error delta between time series and piecewise affine executions. The fourth column shows the number of modes in the final hybrid automaton model. The last 2 columns show the number of explored tree nodes with respect to the total number of possible tree nodes. As expected, decreasing epsilon results in bigger models, since existing modes can be served for different piecewise affine execution pieces less often. In the ECG benchmark, we observed that decreasing delta can result in a smaller hybrid automaton, since the constructed piecewise affine executions are less diverse, even though they have more pieces compared to. The runtime is mainly influenced by the depth of the exploration tree and hence the length of the pieces, but we observe that the algorithm never comes close to exploring the full tree. Summarizing, we have developed an automatic synthesis of linear hybrid automata with affine dynamics from piecewise affine functions for the case of synchronous switching. The synchronous problem can be reduced to an adaptive membership-based algorithm. A feature of our algorithm is that it works online, meaning that the functions f are processed sequentially and we only modify the intermediate automaton models. For future work, hardness of the membership problem for the class of automata that we consider is open. We currently do not know if that problem is decidable, and if so, what complexity is required to solve it exactly. Another interesting but challenging extension of our work is to allow for transition switches, not at a single time point, but in a whole time interval. Thank you very much for your attention to those who have reached here, and I will be happy to answer your questions at HSCC.